So anyways, the file system is basically what automatically keeps track of the data for you. It makes it user-friendly. I specify names and it figures out where on the file system it is. And this is the stuff that's internal to a database engine so that it can do it itself. So on a database engine, it organizes the data in raw partitions on its own and does not depend upon the file system characteristics, inodes and directories and stuff. And we're hoping that when we allocate stuff on the file system interface, XFS, is going to try to store the files contiguously. And it's one of the reasons I don't like to run into sites that have full file systems. As the file system fills up, it's hard to find contiguous space. And when I was at Disney, 98% full and they're doing video work, you know that they've got fragmentation as a problem. And I'll show you how to get fragmentation metrics, number of files that are in pieces and stuff. And again, if a file like a video movie is fragmented all over the place, then I've got seat time as I try to catch up with my video frames, and the customers in the hotel rooms might start dropping frames and stuff. Where?
No, it finally came up.
Okay. I didn't grab the operator console, it was stolen from me, and I just rebooted from a normal window. So file systems are created with partitions that are a single partition or put together as a logical volume with multiple partitions. Again, there are two types of logical volume managers now, XLV and XVM. And XVM will probably replace XLV at some point, but XVM is for CXFS, for distributed file systems. We're not really going to talk much about CXFS, but one thing I might point out right now, with CXFS, our metadata that we're talking about here right now is locked to one of the servers within a cluster. So with CXFS, we may have 10 systems that are sharing a common file system with hardware switches. But only one of them maintains the file system characteristics for a given file system. So each file system has a server responsible for keeping track of all the metadata. If a different system within a CXFS cluster wants to change something in a file system that's controlled by another server, it has to talk to that server and get permission to manipulate the metadata, to grow or shrink a file, create or destroy a file. So there are tokens passed between the servers within CXFS. Okay. That means that whenever I've got systems where files are constantly being created, destroyed, growing, or shrinking, I have to talk to somebody else to get permission to do that. That's going to slow down those sorts of markets. Okay? So if you, for example, have a news server with 10 hosts in it, one of them controlling the file system, every time one of the other hosts has to do something, it's got to check with the server that controls that file system, make sure they can do it, lock the file or lock the metadata, and then make its change. So I would not advise CXFS, for example, in a news server environment at this point. So all this metadata in a CXFS environment has to be synchronized, and there are tokens that are passed between each of the servers that are sharing that common file system. So anyways, at the system level, we've got the super block and we've got the data. The super block was created by what? I know. MakeFS. When I make a file system, the super block contains the attributes that are on the MakeFS command. How can I read the super block conveniently? What command is going to pull out the MakeFS configuration?
XFS GrowFS.
Correct. XFS GrowFS. So in my inventory process, XFS GrowFS would have grabbed the block allocation and size, do I have external logs, all that sort of information about this particular file system. So it's XFS GrowFS, there's a -n option that says, just extract this. And if I want to change it without a reboot, that's what GrowFS can do. I can change the block allocation sizes and some of those sorts of attributes. Okay?
Yeah, I think, isn't it pretty important though, you gotta have that n in there, otherwise you mess things up.
The end it says read it, yeah. Otherwise it will give you warnings that you're on active file systems and stuff like that. Or you could, yes, MakeFS could overwrite things, but GrowFS would be fairly safe without, if you forgot the -n.
Your system was on the wrong kernel.
You're right.
RFS, it doesn't touch actually the data, right?
No, it's not touching the data, but it can change the attributes of the superblock. Thanks, Warren.
Sorry to interrupt.
No, you're right. Let me get it done. So you can also see, so I'm going to do systune. And buff was at 400, so I'm going to set it up. And I was just arbitrarily picking a big number before, and I'll just pick a different one this time, 100,000. Okay, quit. If you cat the var sysgen stune file, you can now see that that system change is documented there. Okay, which we didn't look at it before, but we saw it earlier in the week. Okay.
Now we have to boot.
Gotta make a new kernel first.
Okay.
If I don't do this, I'll have to reboot twice. It'll catch it the next time I come up. In fact, one of the things I should show is ls-l / Unix. We have a unix.install that just got created by system. One of the things that bothers me, my path is picking up a 7.2MR compiler. I'm not sure whether I would like to use a newer compiler. And that was an environment variable change. Whatever my root environment has here, that's been set up somewhere.
The new about the 10,000,
I think that was 100,000.
100,000.
Okay. And again, I'm using a big swing, but I have no problem with setting this really big. If the users want the memory, go ahead and push the kernel back down. That will happen real quickly. We're going to see that. Okay. So if a customer has a 38 gig kernel, they can pop up buff view and see what that data is. If they don't like it, they can push it back down.
Those buffers are dynamically allocated in the RAM at the startup?
Yes, but it grows and shrinks. This end buff, older Unixes, it was a static table, so if I set it too big, it took up too much memory. Okay, but now with IRIX and Linux, they both grow and shrink. So you've got a ceiling and you've got a floor. So I'm raising the ceiling on the kernel. Okay, but it's not an actual allocation, it's simply the total number of headers that I can have on my system.
Oh, okay.
Okay. Whereas older Unixes, it was actually an allocation on boot. So this will grow and shrink, and it will be allocated across all nodes round robin. It will not stay on just node 0. Now there are things on node 0 that do stay there, but network buffers and file system buffers are round robin across the nodes. And we'll see a little bit later with CPU set, I can keep the kernel off my node. If I don't want the kernel to take memory from my node, because I've got something locked down in there, there's options to do that with CPU set. So setting nbuff large simply says this is the total number of buffers that I can have in my system. And depending upon what the load demand is, it will grow and shrink in the physical memory allocation. We're going to see that with gross view and a few things like that. This is probably the most common, in my mind, the first thing that I would do on any system is up it. On my workstation, anywhere, I'd make it as large as I can make it. This is a 6.5 issue. Now this stuff will vary with every overlay in 6.5 that I've tried in terms of how quickly it shifts data between different pieces of the cache. But it always will push the kernel back down when needed. So that's the real question. If I want the memory, can I use it? I logged into a system, 64 gig of memory. It used 2 gig the whole month. And it had I/O problems. So there was 60-some gig of memory in the system that was never used throughout the whole month at this site. They could have upped nbuff and used that memory to hold inodes, directories. They could have used the memory in other ways. Okay. But again, politically, if they don't do I/O, let's use the memory for real work. But in this case, they basically oversold the memory. So why not use that memory? Even on my workstation. gr_osview-d. It's the rmemc display and the rmem display that describe how big this kernel is growing. down here in the blue, it's kind of hard to see here, the blue is the kernel. And then we've got our metadata, which is the light blue. And then we've got clean data that's sitting in our buffer cache. And then we've got free memory, and then we've got some user space. Looks like somebody's running, oh, this is my workstation, that's right. That user space is going to be visible with something like GMAM usage or PMAM to find out what that was. And most of that is Netscape, as I suspected, being a workstation. Okay, so this is also showing the same thing, except the pieces of the kernel that we're going to talk about later are all buried within the kernel itself. And if you click on the kernel, then you can see that break up a little bit more too. Question?
Change stuff just a tad bit. What is it about Netscape that's causing it to keep growing and take up all your space if you leave Windows open?
I haven't looked at what it is. I don't know.
It's a holiday. I mean, it
Yeah.
just keeps growing and growing and growing.
Yeah, I don't know what it's holding or whether there's memory leaks. I haven't looked at that at all. The systems I work with is generally not a Netscape type system. I was going to click on IRIX, and then here's my buffer cache, here's my metadata, and here's the heap for all the programs that are running. And then various pieces like network buffers, page information, kernel tables, and some general kernel space. The executable down here, the actual kernel executable is right there.
What is the heap mean?
What is which? The heap? The heap is when you're growing and shrinking. The heap is where a program, there are different types of heaps. There's a kernel heap and there's a program heap. And these are where malloc basically grows and shrinks the heap. So when I need memory, I ask the operating system to give me memory. The place that I allocate it from is called the heap.
Oh,
And the heap
okay.
may grow and shrink. So a program may have a heap because it's got a 1 gig array, so it asks for a 1 gig off the heap.
Okay.
So this is the data portion of a program, or the kernel itself also has a heap. And the stack can often be allocated out of the heap too. So when a program does a subroutine jump, the heap has the stack that grows, and the data grows, they kind of grow towards each other. This is stuff that's actually in the IRIX functional overview class showing how the heap and the stack out of the data portion of a program or within the kernel allocate the stuff. So whenever I need memory for a subroutine, because I'm going to jump off somewhere, I have to save all that stuff in that subroutine, and I push it onto the stack, and the stack is growing into the heap just like any other malloc that I would do to ask for memory. Now the kernel doesn't actually do it as a malloc, there are subroutines the kernel calls to get memory from the heap. Whereas a program is malloc to do it, to ask the kernel for that growth. So I just want to be careful because there's a kernel heap that we're looking at here, and then there is a program heap as well. And that was the BSS space that we talked about yesterday for a while. So code 4 is allocating out of the heap a lot of memory space, but not actually even using it all. And you can even have kernels that have memory leaks, and the heap will grow. And a reset will often drop the heap back down again. That's one disadvantage with SGI is we don't run our systems for a month. They're taking so many reboots for administrative reasons and trying different release levels that we don't see a kernel that runs for a month and watch what kind of heap growth there is to it. Customers do. If it's running for a year, they see that heap growth. So that's what we're changing now is the ability of that kernel to grow. So the FSCTL, dirty, clean, and what's called free C can all grow. But I want to come back to that later. What I needed to do was,
No, you haven't rebooted.
did I reboot yet?
No.
Thanks. So this is one of the things that I like to do first because there's nothing wrong with letting the kernel use that memory if nobody else needs it. If I set it too big, it's not going to hurt me. The kernel is going to drop it back down and say, you set it too big, fix it. Okay, so we'll see what it actually comes up as. 100,000 is what I asked for before. And I'm going to pop up buff view just before I quit, so we still see 400 there. And again, this is all the data that's in that buffer cache, which right now is all system data. There's the buff view binary. All your executables are in buff view too. Every time you do ls or sh and stuff like that, those are loaded through buffer cache. So your shell is pulling in all your libraries, all those sorts of things. So for example, just before it shut down, all this stuff was system type of stuff. If I ran code 3, it'd push all that stuff out and replace it with the temp files. Now if I try to do VI, I have to get that binary file system through this resource, but somebody's just filled it or using it, and I can't get a buffer. It's what I call dominating file system buffer caching. An application can come along and hold those buffers, keep them busy. Okay, you don't lose a buffer if you can keep it busy. But an interactive user can't keep VI files busy very well compared to something that does not have a human tied to it that's sitting there just reading the data and processing it and then rewriting it. Okay? So this particular behavior can be real harmful to the interactive user. Because now my SH and everything else, if it's not in memory as shared text, I may have to go to the file system to get it. So we were just basically looking at superblocks, and I got distracted by getting our system increased with the buffer cache
So
storage.
those buffers really where all the information goes before you go to disk, right?
Yes.
That's what it is, basically.
Basically everything that's going to disk by default. Now there are things that are bypassing buffer cache. I guess we didn't really talk about that up here, but there's also whether it's direct cached or direct. So for example, in the database, or raw, as we call it, character. The database market uses raw, and none of that data is going through this. So different markets do different things. Now in terms of INN news server, the news articles and everything are going through this. It's doing buffer cache I/O, very little direct I/O. But then you take a command like find or file system backup, CPIO tar. Some of them will show up as direct I/O. They have to do direct I/O. Is it back up yet? See, on my workstation, it's all my interactive type of stuff. In fact, fonts are in here. The showcase file that I'm using up here, this thing right here, that's it right there. Right now it's using 2 buffers. The size is 128K. That's how much memory this particular file is taking in my buffer cache.
Now, did you increase that to 100,000? Why it's saying 919?
This is my workstation. We're waiting for the boot, and Warren just gave me the thumbs up on it. So do is now up. And again, this is right after boot, so buff view. And it did pick up 100,000, so it wasn't too big for the kernel to reject. But if I tried that on my workstation, it'd be too big. Your workstation, the largest it can go to is 6,000 on a 32-bit kernel. On a 64-bit kernel, 600,000 is the largest that it can go to. And again, everything in here is system type of stuff. A lot of the stuff even coming from boot. I would assume iCrash was in there during the boot process. We looked for things, and it's still sitting in there. Anyway. So I need to get away from the buffer cache story and get finished with this chapter. But we were talking about super blocks and basic blocks. Then there's the Inode tables and Inode free lists, and this is keeping track of where our files are on the file system. And then we've got our actual data. Now data is allocated in what's called an extent. For older Unixes and for Cray type of people, it was all bitmap based. We had a bit to describe every allocation unit or every block of allocation in the file system. The allocation block size was determined by your make FS. So with XFS grow FS-N, we'd see that the default block size is 4 kbyte on IRIX. So in older days, we'd have a bit describing every 4 kbyte. That would be a bitmap-based system. But nowadays, we've gone to extent-based systems. Windows NT, Linux, we're all extent-based systems now. Because as the files got bigger and bigger, the bitmaps got bigger and bigger. And this is important because we're going to come back to this. Older Unix type people, like crate people, would up the allocation unit size, the block size. And that has its side effects. It could be worse than the original problem because there's a whole bunch of alignment boundary restrictions that also get larger when you start upping the allocation unit size. Now in older days, we'd up the allocation unit size because then it'd be quicker to allocate and deallocate. So if I had a gigabyte file and I was doing it 512 bytes at a time, it'd take a long time. Plus I get fragmentation. But nowadays, since we're not bitmap based, increasing the allocation unit size doesn't help you allocate any faster. We don't have as many structures to check and manipulate and to grow and shrink. So with an extent-based system, you simply point to the beginning of a contiguous piece and the number of blocks to it. Okay, so you could have a 400 meg file that had a whole bunch of bits to it and take up all your memory to describe the file, or you could have just one pointer and the total number of blocks to the file. Now we'll come back to that, but there's a command called XFS bmap that prints out the extent list and can show you if your file is contiguously allocated or not.
I thought that somewhere told me once that there's no such a thing like, like fragmentation.
Oh, there is. You always have fragmentation will always be a fact of life.
I remember one time.
Marketing people will say it doesn't fragment it, but that's not true. Okay, if my file system is running full, fragmentation will be a fact of life. And that's why I like to keep my file systems. My threshold is 70%. I'm going to say something.
Oh, that there is nothing, to actually fix that. Like in Windows, there is this defragmentation.
There is a defragmenter. It hasn't been completely reliable because it's fairly new.
There is no the command XFS underscore FSR.
Yes.
What it does, it defragmentates.
To rearrange the nodes.
No, the data itself.
The data.
It will reorganize the data itself. It will defrag it, just like you have on Windows. You have a defragger. Now, I defragged my disk once, and suddenly I had a half a second blip of one song in the middle of one of my other MP3 files, and it defragmented poorly. It just kept going and stuff. So that's one of the disadvantages. Now, you'd like to avoid fragmentation in the first place. Now, XFS does everything it can to avoid fragmentation, but it is still always going to be a fact of life. And it's more a property of a variety of things, like the size of the files, how the file system is configured, and the intensity of the I/O. I'm going to talk about fragmentation again, but let's go back to this. But you're right, XFS tries to avoid fragmentation, but it will always still occur. It's just a fact of life. It depends upon how much you're pushing your file systems. And that's why I don't like to see 98% full file systems. The customer will say, but it's a 10 gigabyte, or nowadays that's not much, a 10 terabyte, 100 terabyte file system. But it's still full. Okay. Anyways, there's a lot of detail about this in a couple of other classes. I'm not going to spend a whole lot of time except for what's in this workbook. At the user level, we just see it as user files, we see it as directories, and we see it as device files. And the device files are how the database interface works. The character interface is when you're using the dev disk, dev hard disk type of interfaces. So inodes are what keep track where things are on disk. Different types of file systems have different structures to them. Now there are two copies of inodes. There's one on disk, and then there's one in memory. It's the one in memory that we've been calling the metadata, file system control data. So there is a working copy in memory, and I can see them with buff view. Buff view shows this metadata here to summarize them as system. So this has 597 buffers for the metadata of my file system. And some of them are going to be inodes. Some of them are going to be allocation group information and directory information. If you do an F option on BuffView, there is an INO flag that will show you just the inodes. So now I'm actually looking at every inode that's in my buffer cache, in my file system buffer cache. And this INO flag shows that it's an inode, and these are actually something that's been modified and is in a delayed write state. It's going to flush out the disk at some point. There, we just had a flush. The WDW flag just went away. What's controlling when that flush occurred was this VFS sync, except it's spelled wrong. It's VFS R sync, if I remember correctly.
How do you enter a command in BuffView?
Do a question mark and it'll give you help. In this case, I just typed in an F. It's VFS sync R. So in your workbook, you need to put an R on the end of that. So with BuffView, I was actually looking at those buffers. Okay. And if something had been modified, I don't see any inodes that have been modified right now. There we go. So these are some inodes that now got modified, and we're waiting for the delayed write activity, and there's going to be a, what did we have as a default here? There, we just had a flush. Some went busy as they were being used. It's a 30-second. I don't know if that's the same that we've got here. Let's check.
Is that why the system disk usually flashes every 30 seconds or so often?
Well, that could be a variety of things, including cron events or something like that. But there is going to be a flush periodically. Two types of flushes are occurring. But if there's nothing changed, then you're not going to necessarily have disk activity. But that's a pretty quiet system, so. Okay, so my VFS sync R was every 30 seconds. So looking at this, I get it just says system as an Inode number. I actually see the file system then. And if I was NFS, I'd be able to see NFS activity with BuffView as well. NFS traffic is going through buffer cache. For example, here I had an inode that was in do/ptemp, underscore ptemp. This then is the actual location in the buffer header chain where that inode was allocated. So I had on do 100,000, this was buffer number 1889. In that was the actual slot number position in the table. And these inodes are right now taking up 8K within buffer cache. We don't know the size of the allocation on disk. This is what it's using in buffer cache. Don't really care about the offset. And then the age is, what's the age? What was the last time that inode was referenced or modified? Or if it was data, last time that the file was touched. And it's the age that is used for the busyness. So if it's more than 5 seconds old, then it becomes aged and no longer is marked busy. And then somebody can take it from them. But if some program keeps modifying that buffer and the age stays current, they can hold that buffer and dominate it. And it's the least recently used algorithm, so me as an interactive user can't log in. Because I can't get a buffer because somebody else is dominating all the buffers that I have. I have been marooned from getting these buffers. So anyways, 2 copies. One is on disk, one is in memory. You can actually go through the disk ones. You can count them. There's a command called xfs_db that allows you to chase through the inode locations out on disk and stuff. Anyway, let's go on. So XFS is a journal file system. The journaling is to save and protect the metadata integrity so that if I take a system interruption, I know what files are being modified. Particularly something like a news server where everyone's posting articles 24/7, you know, on all these news articles, MP3s and all that sort of stuff. I don't want to have my news server take an interruption and have to rebuild a very active file system like that. I consider a news server to be a very busy metadata environment. Probably your busiest of all the markets. Also XFS, there's no performance penalty as the file system grows. As I get bigger and bigger, and that's what I was talking about yesterday, the recovery time does not increase with file system size because I don't have to go through the entire file system tree and check integrity. I've got clues as to what was changing. So the journaling is overlapped with my I/O, and I don't really see the penalty as long as the journaling doesn't slow down my interactive or my file system changes. And yesterday, we finished yesterday talking about OS view and locks that would show that the XFS log was slowing me down. Okay, so we saw that XA sync argument that said, I'm waiting for a flush of my log. And if that keeps happening, then the log could be something hurting me while I'm running. And that's when we would go to external logs. Inodes on the system are dynamically allocated. They're variable size, smallest would be 128 bytes. You can go larger than 2 KB, I believe. Zoom in on XFS, MakeFS. Other one around. Other way around.
Underscore XFS.
Data section size, inode options, the size right here. Yep, the maximum is 2 KB for an inode. Okay. Now, there was something else that I've got to talk about. I don't think it's in the workbook. And that is a new option that was added while we're talking about metadata. That is the version number. Right here. You now have the ability, and this was because of a couple of benchmarks we lost at AOL, for example, and a Latin benchmark too, where a sendmail experiment was running faster on Suns than on the origin. When you're naming your file system, you can also specify now a version. Let's just go with that. This is akin to the Cray Unicode primary-secondary partition concept, so that the primary partition would be where all my metadata is, and I can go to a small block allocation unit size, and then on my secondary partition I can go to large. Except this is kind of the other way around. If I have a large metadata environment like news servers or mail servers, I've got lots of metadata. But the data is small. With version 1, when I increase my allocation size, both the metadata allocation size and the data allocation size are the same. So when I'm upping my allocation size, my metadata allocation size is also going up. Okay? But the other way around, on a news server, I want a small allocation size, but now I've got a small allocation size for my metadata. So with version 2, I can make them different. So with version 2, the directory block size can be any power of 2 up to 65K. That way, one allocation size can hold lots of metadata, but I'm not wasting space for the actual data that might be 2 KB in size. And on a news server, there are a lot of posted articles that are less than 2 KB in size, unless you're looking at MP3s, binaries that are being plugged into news groups. So when I switch to version 2, I can make the directory block size different than the data block size. Okay? So if I have a file system with lots of little files and a directory with lots of little files, I'd like a large directory block size, but they're little files, so I'd like a small block allocation size. And maybe the other way around, I've got a file system with a few large files, so I'd like my inodes and I'd like my directory blocks to be allocated small, and then my files themselves allocated large. So it goes back to knowing, do I have lots of little files or a few large files, answering that sort of question.
In DMF, when we increase the inode size, it has also automatically increased the block size. Are you saying that this allows that not to happen now?
Correct. That's what they're saying as well. When they're, I'm not sure about the dependency. This was not the inode size. This was the data block size. Let's just see what it checks on the inode.
On my DMF class, I had people up the inode size to 512.
See, I don't think that's going to affect it.
Well, the block size had to be 1024 with an inode size of 512. It wouldn't let you keep the same block size.
But yeah, this is not this is directories and data, not inodes and data.
Okay.
So this was for the example, if I spam my system with 200,000 email, a user, or 200,000 users get one email spam to it, then I'm going to have 3 inodes per send mail handling. There are 2 in the MQ directory. One is a locked inode, and then one is the actual data inode, and then one in user mail. So in that send mail experiment with 200,000 users, there was almost 600,000 inodes that had to be created and destroyed in the same directory. So this is the concept where I have a large directory with lots of files. So in that scenario, they're sitting there spending all their time allocating and deallocating lots of little pieces for directories that really need to just get one big allocation. So that's what this was developed for. Now you were saying changing the inode size, that's not going to affect this one. This was to isolate the directory and the data. So they'd isolated the inode in the data, they hadn't isolated the directory in the data. Okay? So those are the types of markets where I have directories with large numbers of files in them, and I have directories where the data is being changed. The files are growing, shrinking, being created, or being destroyed. In other words, there's inode changes going on all the time. So send mail servers and news servers are the most common markets for that. Whereas a web server generally isn't, because web servers pump their data to the machine and then everybody just is reading the data. Okay, unless it's a web server that actually has satellite data coming down and we're writing as much as we're reading. And even in that scenario, you generally don't get directories with large numbers of files in them. So this version concept was designed for those 2 markets. So the block size is specified as a power of 2, or in size. The default size of version 2 is 4 kbyte. Okay. So I can, with version 2, up my data size, and for example, on the video server, make my allocation units very large, and not waste information or waste space for the actual directory that contains one file name for the video. Now it also mentions that the block size for the file, for the data, is larger than 4096, the default value for the block size. Okay, that's good. So as I up 1, the other one goes up 2. You're able to separate them out. So in version 1, the directory block size is the same as the data block size. Hopefully I haven't talked myself in a circle. So these inodes are dynamically allocated, and I was then talking also about the directory information. Also, this is what Janet was just talking about. Small files and symbolic links can be stored directly in the inode, and by increasing the inode allocation size, then we can get more information in the inode. Now I don't have to follow a linked list or something like that. So on a news server, some directories, it would make sense to have large inode sizes, because the news articles are less than 1,000 bytes. A lot of the news groups are just posting very small things. The trouble is some of them also have very large files in them. MP3s and videos are even being plugged into news groups now. Now XFS, this is what we've been talking about right now, has variable block sizes. And I was just talking about the fact that we can separate our directory block sizes from our data block sizes. And also we were just talking about that the inode block size can be also different. So we can go from 512 bytes to 64K bytes. When you go to a real-time partition, the block size is designed to be a larger allocation unit. Real-time subvolumes are meant for large sequential I/O. And here's what we've just been talking about, faster algorithms for inode access and directory searches. One of the things that's happened in these file systems is we no longer have bitmaps to chase through. We have what are called B trees. And a B tree has a second key, a hash key within it, so that when I'm tracing down a B tree, I've got clues as to which branch I want to take. It's kind of like having a sign at the fork of the road and it says this is the direction you want to go. And it's kind of like an alphabetical hash key. So with B trees, before I'd have to hash the whole tree left to right alphabetically. Now I can say I'm looking for M. So as I go down the trees, I can find what I'm looking for through the B tree. Now there's some better examples of B trees in some of my other class materials. I'm not going to go through it right now. But that's what they mean by faster algorithms, using B trees. And also the directory search process too, going through the version 2 directory, for example. So having version 2 allows us to have less performance penalty for directories that have large number of files, or even large file names. Okay, if I'm going to large file names, that also takes up space to describe my file. The other thing that we have within XFS is something called an allocation group. The purpose of an allocation group primarily is to allow me to have metadata changes occurring separate within each allocation group. So if I create a file in each allocation group, their metadata can be changing in parallel. Now unfortunately, the way I round robin is when I do a make dir. Every time I make a directory, I go to the next allocation group. Also, there's no way to tie these allocation groups to physical drives. Like in the Cray world, we could go round robin and make sure that each partition is a separate drive and simply rotate the files across these drives. And we can do that by first directory, by file, or by any directory. So in XFS, it's by directory. Every time I make a directory, I go to the next allocation group. So that's going to be bad for some environments where suddenly, like on a sendmail experiment, all my directory information is in the same allocation group. Var spool MQ is the same directory. Okay. Also, if I set too many allocation groups, if one allocation group is filling up, I now have to work harder. And if there are more allocation groups, I have to round robin between more allocation groups trying to find a contiguous allocation. As file systems fill up and I have lots of allocation groups, my system will actually start throttling back as I spend more time trying to solve the fragmentation problem than actually getting the work done. So you can get into a bad situation where you get too many allocation groups. But I wish the allocation groups could you could control it by file or other options other than just by every time I make a directory. So a news server and a mail server would benefit from those sorts of capabilities. Now the super block is only used off the first allocation group, but there is a copy of it in all the other allocation groups, and it's possible with the debugger to get to those other super blocks. But the main thing is that each group has its own inode and block allocation. So each allocation group can have files growing, shrinking, being created or destroyed at the same time in parallel. But only one per allocation group.
That's where I do talk about separating the files with version 2. Or it's not? It doesn't
No,
have to
well
do
with
that.
version 2, there is within this the name information, the directory information. So version 2 only affected that. But with MakeFS, version 2 is one of the options on MakeFS. One of the other ones is to say how many groups we want. So each one of these groups has its own, what we call a name cache, where all the actual names point to the inodes, and then the inodes point to the data. But the name information is not in the inode. The name information is in a separate structure, and that's called the directory name cache. DNLC, directory name lookup cache is another name for it. Let's just go on here. XLB then is a layer on top, or I should say underneath XFS, and allows file systems to grow larger than a single disk. It would be called a volume manager. So there's a newer replacement port called the XVM, Extended Volume Manager, XFS Volume Manager. This allows me to put together my file system in 3 different ways. I can plex, I can concatenate, or I can stripe. And concatenating is often referred to as a volume set within Windows, for example. I just build the file system, make it larger. And then an XLB is composed of 3 subvolumes: the data, the log, and potentially the GRIO, real-time partition. Now, GRIO is designed more for the multimedia market, the real-time market. It's designed for large sequential I/O. It's kind of like a secondary partition concept, except that the operating system doesn't automatically use it. The program has to make calls to use it. So there's no scientific market applications I'm aware of right now that use the GRIO subvolume. One application I do know can use it is MediaBase. So with MediaBase, I would put all my metadata, my inodes, and my small files on the data partition, and then MediaBase would place the actual video assets on the real-time partition. Okay, and the real-time partition has got larger allocation in its sizes and is designed for large sequential I/O. Remember my crossover story? Seek plus latency times bandwidth. Or on the marketing slides, I'll talk about a video drive or a database drive. So high crossover drives would get placed on the real-time partition because that's what they're designed for. And then the lower crossover drives would be better on the data partition. And a log partition would also be a low crossover situation, lots of little I/O. If every drive I have on the system is the same, crossover doesn't matter to me. But if I have different types of drives, they have an advantage or disadvantage to the latency bandwidth question. So a log in the data, I want latency. I want to get to that inode real quickly. But if I've got a video movie, I want bandwidth. I've got a lot of data that I've got to deliver. So my lower crossover drives, I'd want where I need latency, and the higher crossover, the bandwidth drives, I'd want where I need bandwidth. And that's what real-time volumes or subvolumes are about, is bandwidth, not latency. And also then with striping, the guaranteed rate I/O would be a striped situation in most cases, particularly with a media-based video server, because I'm doing large sequential I/O. But the log, for example, would probably never stripe because the log is lots of little I/O. The data, it would depend upon the nature of the data subvolume. If I don't have a GRIO, I might stripe data. That's what's usually happening in the scientific market because the applications don't know how to take advantage of a real-time partition. Something we need is a sign command to have a GRIO layer and a real-time layer to use the real-time partition. Now it says here, disk striping for potentially greater performance. That's a matter of matching the stripe width to the I/O request sizes. And Warren, on your machine the other day, we turned on the stripe statistics. It'd be interested to check to see what they look like these days. Maybe you can mail me a sample of that now. Unless there was a reboot. If there was a reboot, then we would have lost data. So if you come up and it's turned off again, it's probably been rebooted.
Oh, I doubt that was true.
Yeah.
Yeah, they were starting to beat it yesterday, so.
If we've got striping statistics to tell me how well I'm matching the stripe geometry. Maybe we'll get back to that in a few slides. Let me save that. So Warren turned that statistics on to say how well is my I/O request size is matching the stripe geometry that I put together. Do I equal stripe width? Am I smaller, larger? How, of all the I/O requests, how do they break out into my statistics? So if I have a server that's reading satellite data down, I've got a constant steady stream, video stream coming down. I want to set up a file system just for that video stream and I want to figure out the size of the request with either PAR, or we can figure out the size of a video frame and estimate it from that. And we'll go through that example. And then I would want that request size to match exactly into the file system geometry to match the stripe width that I've set up. So this is like my fire bucket brigade. I want every bucket in the fire bucket brigade to be full to the top. I don't want to overfill them or I don't want to underfill them. I want to be hole-friendly numbers in this fire bucket brigade. And 64 kbyte was the default. But in the video market, we like to go up. In the database market, we like to go down. 64K was just picked as middle of the road.
It's so amazing, but most customers, they don't. I mean, we get a lot of calls with XLB, and I basically always ask, you're striping, what is at least your average of the, file that you're putting on those,
Right.
in that file system? They don't know.
No, they don't.
Then I don't know, and I'm like, okay, so we use the default,
Yeah.
But I guess it's not my responsibility, it's theirs.
There is a point where it becomes a value-added service in a professional service situation where they pay for tuning their system. If they have a performance problem, then we generally are responding to it. Now, in your particular question, there is a man page to point them to it as an example. But I was going to save this for this display, but the slide coming up. But disk align is a good man page to talk about disk striping and how to decide how to stripe. Now this was written for the video market, not for the database market, because the database market doesn't always stripe. So the examples here are for the video market. But to answer your question, they really need to run PAR and a few other things and look at the request sizes that are coming from their application. So it all depends upon the customer. If they spent $100 million on a large system, the support staff there know how to do it. If they spent $5,000 on a home system and they're doing video work, they don't know how to do it. So it is a trade-off between the high-end compute server sites and the mass media market that's doing web serving and database serving and the other types of volume markets. But disk align is a good place to start. But I do feel that people overstripe. They think striping is for performance. Striping is for bandwidth. The trade-off is you may waste latency because you've locked all the drives together as a single drive. If I don't get all the drives active in parallel at the same time, I'm wasting bandwidth that's potentially there. So I gave the example the other day of a customer that bought a 100 megabyte rated RAID cabinet, but then they only got 40 megabytes out of it because they did not match the request sizes. And then once the analyst went out and dropped the geometry of that RAID cabinet to a smaller size, they got the specified bandwidth that they were looking for. Or in other cases, there was another command called disk perf. That is a way of stressing the file system, and it will specify what your request sizes are going to be like in ranges. So -R and -M actually specify what's the request size and what's the max. So I could start off at a 2 kbyte request size and go up to a 64 megabyte request size. And a drive is not going to behave flat across all those request sizes. You actually get what often looks like a sawtooth pattern. Okay, so at hole-friendly numbers, you're at maximum bandwidth. So this might be 16, 32, 64, 128 kbyte. It's just that computers work in powers of 2, and those numbers happen to be the friendliest numbers because of the way the hardware works on powers of 2. So these are your common request sizes. Now if I did a 6 kbyte request size, I'm not going to be able to fill up the bucket the whole way, and I'm going to waste some bandwidth. Now newer drives have caches that can hide some of this stuff and smooth it out so that we can overlap it and hide it with a cache within the RAID cabinet. Okay, but there's still going to be a sawtooth pattern, so when people stress these file systems, stress disk drives, they always like to pick powers of 2 numbers, but then the application may be doing something else. And and you're gonna waste some of that bandwidth. So disk perf is designed to actually range from the smallest to the largest. You say, what request size do you want to start at, and what request size do you want to end at? And then it's going to pick hole-friendly numbers to do that. Now let me go back to disk align for a minute here.
Okay, stats, you got the email for the stats right now.
Great. With disk align, it does go through an example here. And it's got one of the things you got to keep in mind with striping is that there are alignment restrictions. Okay, everything has to be hole-friendly number, common denominator in sizes. So everything is a 512 byte block, and then on top of that you've got block allocation size or the file block size. That was what we were just talking about a minute ago. If I up that, I'm also upping my alignment geometry. I said a little while ago, older crate people will up the allocation block size because they did that in Unicode for faster allocation. But now in IRIX, that's not a good thing to do because now your alignment restrictions are also getting wider. The hole-friendly number, common denominator, is getting bigger. And you're not getting faster allocation because it's not bitmap based, it's extent based. So that's an old habit that has to change with extent-based systems versus a bitmap based system. And Unicode was still bitmap based. So there are alignment restrictions. You got to be minimum request size to the device, you got to know the file system request size, and you have to be multiple page sizes if you're doing direct I/O or gather scatter type of I/O, which is LIO, list I/O. And here they're just talking about a typical 16K page size being the multiple hole-friendly number that I have to be a common denominator of. Now in this example, they went through a calculation. So they looked up, they're looking at a video frame here called CCIR 601, that's a standard. So they already know what that standard is, they looked it up, and it was 720 pixels by 243 pixels, and there were 2 bytes per pixel. So out of that, they calculated a typical request size. They said width times height times bytes per pixel, and they came up with 349,920 bytes for every video frame. Now, par would have been better. They should also in here, instead of calculating the request size, run par-s, and we were looking at that yesterday with par-s, what our request sizes were like. In fact, we used SPV's par button and then looked at the spread of request sizes. So once I know that, then I can figure out what my alignment's going to be. So, with disk align, they specify, I want the file system to be called video. The customer can pretty much handle that. This is the number that they don't understand. Okay. So with either par or calculating it, they have to figure out what is the request size I want to optimize the file system for. That's the piece that the novice doesn't have. Okay. So here we calculated it, but it's much better to use a par-s to figure that out. And here's the alignment restriction that I've been talking about. If I upped my block size, like we saw earlier, my stripe alignment has to be a hole-friendly number of that, and my fire buckets are scaling bigger. So when I increase my block size, I'm also increasing my stripe geometry size, the hole-friendly number multiplier. And some people will up it to 64K bytes, and now my stripe geometry's gotten real wide. They also then specify the drives. The disadvantage here, and Warren was talking about this, is that we're not round robining among controllers. The stripe group is down the same controller. I would rather make sure that it goes round robin. First disk of the stripe group on one SCSI, second disk on the next SCSI, third, fourth, then maybe round robin back. But as I fill up the fire bucket, then I overflow to the second drive, then to the third, then to the fourth. I want to round robin them across my SCSIs. If I can't make a request size large enough to break into the whole stripe group, then I go to the first drive, then the second drive. If the second drive's down the same SCSI, now I'm loading up that SCSI, then I'm loading up the next SCSI. So I could have a I request size that only fills up 4 of the 12, and now I'm just filling up 1 SCSI. So in this example, they're down 1 SCSI, but I would rather round robin them and buy the SCSIs. Striping works much better when they go down their separate hardware paths. So out of disk align, they then created the syntax to build a stripe group. So they had 2, 3, 4, and 5. So they had 4 drives here. Number of devices was 4. I said my request size was 349920. Okay, so here was my desired request size. Disk align found though that the most common denominator between 16K byte and my request size, the closest friendly number was 360448. So that is my aligned request size. So that's the closest fire bucket size is in a power of 2 and is also a whole friendly number of my allocation unit size for the file system. So that's the closest I can come. That means that there is a wasted space of 10K byte in that fire bucket that I'm filling up. And I'm actually wasting 3% of my bandwidth. This is actually computing the sawtooth pattern. Okay, so it's estimating I can't fill that fire bucket up all the way. I'm going to waste some bandwidth in there. So that's a 3% waste. That's what they're saying here. So if I was instead of at 349920, so out here would be somewhere 349920. That would be the whole friendly number, but they're actually a little bit less than that. And they're sitting there at 360448. So it would not be on the other 360448. So they're down about 3%. If they filled it up all the way, if they matched that whole friendly number right on the nose, they would be at 100%. So this would be at what, 97% drop.
But this number is bigger. This is 360.
Yeah.
I'm confused.
But it's just picked the whole friendly number.
360 is bigger than 349.
Right.
Is that,
Well, 349920 was the one that we desired. 360448 was the aligned one.
But I think she's saying the numbers you wrote wrong.
Yeah, I got the
Oh,
numbers
okay.
backwards here.
all right.
Anyway, you're right. So since I can't match it exactly, that's the closest I could get. So, it was,
So that has to be a multiple of 512 or something like that?
512 will be one of them, and then it has to be a multiple of the allocation block size and also the page size of the system. So we're going to have to be 512 multiple for sector size. Everything has to be sectorized. Then we have to be block size too. And by default, that's a 4K byte by default. And we also have to be page size whole friendly number, which is 16K byte. Okay. And if I were to up this, that's going to affect it. So if I up that to 64K byte, for example, now I have to be a whole friendly number of 64K byte. So some people have done that with MakeFS. And now my whole stripe geometry, the fire bucket thing, is getting super big. And if I'm not doing large I/O, it's not helping me. So going back to this example now, the whole friendly number that is power of 2 and a whole friendly multiple of block size was 360448. Now coming out of this line then, it said, let's make a volume element, let's stripe it, and our stripe unit size was 176. So how did we get 176?
I get that's in blocks, right? So they,
No.
Correct.
so they're
That is in
divided.
blocks, that's correct.
Yeah.
176 units of 512 bytes.
Correct.
So you have to divide it, those bytes.
How did we get this? You're going the other direction.
Well, if you
It
have,
computed 176. How did it compute the 176?
you first has to multiply by 1024, right? To take it to gigabytes.
Yeah, but I'm trying to go the other direction.
Oh, okay.
How did we get that? we took our desired, our aligned request size. So we want to design a file system for that that's 4 disks wide. So I'm going to take that
Divided by 4.
and divide it by 4. Yep. 60448. Okay.
So you can know how much you're gonna write in each disk.
Correct. In other words, I want to take that request and break it into 4 equal pieces and send it off to each of the 4 devices in parallel. So I'm designing the stripe group for that particular aligned request size. Did I do the divide yet? So I divide by 4. And I got 90112, that's in bytes. So I'm going to divide by 512. And there's how it computed 176. Okay, so it's saying that 360448 request, if I set my fire bucket size to 176 blocks, that 3600 or 0448 request size will get broken up into 4 equal pieces because 176 is a 1/4 of the size of that request. And then my request will